The only thing left for us to do is a few calculations. So we're going to use the formula delta G equals delta H minus T delta S. And remember, if delta G is negative, it's a spontaneous reaction, and if delta G is positive, it's non-spontaneous. And so there's always going to be that question. So we're given a reaction, we're provided with delta H and T delta S, so we should just have to plug in, and also the temperature, and we're asked if the reaction is spontaneous or not. So the only thing that we also have to watch out for is to convert either kilojoules to joules or joules to kilojoules. So I'm going to take this and say delta G equals, I'm going to convert kilojoules to joules, so 95,700 kilojoules, that's delta H, minus T, which is 298 K, gotta convert Celsius to Kelvin, times 142.2 joules per Kelvin. So that cancels, and I end up with a positive number, so it's not spontaneous. 53,000. Okay, 53.3 times 10 to the 3 joules. So it's non-spontaneous, and because this is bad and this is good, we can overcome bad by increasing the temperature. So we expect the temperature to be much higher than 291 when we solve for that, but we can set this equal to 0 and then solve for T. So T is going to be equal to delta H over delta S, and so we have 95,700. Okay, that should have been joules, obviously, because I multiplied by 1,000. Sorry about that. Divided by 142.2 joules per Kelvin. And so joules cancels and Kelvin comes out top. And I end up with 673 K. So that's the temperature at which this reaction becomes spontaneous. So obviously we expect a high temperature. Here's another one, same calculation, and also questions about spontaneity. Now we have good here because it's exothermic, and bad. So low temperatures are going to make this reaction spontaneous. Okay. So it wants us to calculate delta G, and so this time I'm going to convert to kilojoules. So this equals minus 137.5 kilojoules minus, and this is run at 298 times minus 0.105, because I'm converting to kilojoules per Kelvin. I should have a unit here. This is in Kelvin. Getting pretty sloppy here, but okay. So this becomes positive and counterproductive as far as spontaneity is concerned. And so I end up with a delta G value that is minus 101.6 kilojoules. And that means it's spontaneous at this temperature. And if we do, as I said, because this is bad here, entropy, if we do increase the temperature as it's asking us, our delta G is going to become more positive. Here's a problem that has us use the Gibbs free energy equation, but doesn't give us delta H and delta S. Instead, it asks us to calculate that ourselves based on standard entropies and standard enthalpies. Now those are tabulated, or they will be provided as needed. You just have to apply those or dig them out and then use this formula here. And if it looks familiar to you, that's because we have done this before for enthalpies. You were able to calculate the delta H of formation for a process like this by using the tabulated standard enthalpies of the products and the reactants, and so the phase labels are important here. And then this happens to be the delta H formation from the table here for ammonia, because it is from the standard elements in their natural phase, which nitrogen and hydrogen gas are diatomic and they exist as gases, so those both have values that are 0. And so that's the difference also between entropies here, because these are the standard entropies. Those are absolute values at 25 degrees Celsius and 1 atm for 1 mole. It's just the entropy in that state and not the change of entropy, which is what it is for the enthalpy. So just looking back at one of those tables that we had, and we had pages and pages worth that I handed out to you guys, and we only looked, of course, at the delta H's here. Again, the elements in their natural state are going to have 0 here. These are also deltas where the entropy is not a change, it's just the state. Again, that's an absolute value. And yes, newsflash, we can also do this for Gibbs free energies. So you could, instead of calculating the delta H for the Haber-Bosch process here and the delta S for the process, you could just go to the standard enthalpies, standard Gibbs free energies, and do the same thing. But so here it's all written out for you here, the tabulated values, as I said, for ammonia. Since hydrogen and nitrogen are 0, you would end up with twice the listed value here, and then come up. It's so this is supposed to be exothermic, I guess. Okay, so this is an exothermic process, and you do the same thing for the entropies. You look up the values, and you just have to make sure that you're also multiplying times the coefficients. That's what this n here is. Okay, so once you've done that, you end up with a negative delta H and a negative delta S, and then you can just plug it into the equation here, and you still end up at room temperature. This still ends up being a spontaneous process. Okay, so let's take a look at the standard enthalpies just for another reaction. Focus on those and actually calculate them. So if you were to calculate delta S here, we look up the S's here of NO4, so it's going to be 4 times the entropy of NO, so that would be 210.8 plus 6 times, and so that of water, which is 188.8. So those are our products, and then we subtract from the reactants. So here we have NH4, sorry, it's NH3, so it's 4 times 192.8, and add to that 5 times that for oxygen. That's 205.2, and I left all the units out. All right, so but the units for every one of those is joules per mole per degree Kelvin, and I'm going to have the answer here on the next page all written out. And so the answer here is 178.8. So we have an increase in entropy, right? So yeah, it's 9 going to 10. So we can tell that this is going to have a positive entropy. Let's do one other thing with this system here. We can also look at here we're looking at delta G's. You can do the same thing for delta H's and S's as well. And we can look at the 2 different reactions here, and we're going to be provided with a delta G, but we can use this information because these 2 processes are related to the overall reaction that we want to know the delta G for. And so what you want to do is you want to look at each of these reactions that are provided and match where the products and the reactants are and put them in the correct order. Like here we have iron 3 oxide as a reactant. So if we're going to use this equation here, we need to put iron oxide in the right position, which is the reverse. So this would be 2 times Fe2O3 going to iron and oxygen. And then the delta G would simply be positive 1,484. So we do the same here. We find carbon monoxides on the right side. So carbon dioxide is on the product side. So this is the way it is. But the other problem we have is the stoichiometry here doesn't match. We need 3 carbon monoxides and we only need half of that. So the first one is easier to solve. We just divide everything by 2. And that includes that. And here we have, in order to get from 2 to 3, we have to get to, we have to multiply by 1.5 or 3/2. And if we do that, and I'm going to write it down here, we're going to end up with 3/2 O2 and 3CO going to 3CO2. And that's actually going to work out very well because we want to get rid of this oxygen. And so also I have to take the delta G for this reaction and multiply by 1.5. And that's going to be 742. And this up here is going to be, no, this is the 742. And this is going to be positive, this will be negative, and this is going to be, so it is 771.6. So then all you have to do is add these two up. This is a negative, and we end up with a delta G that's equal to negative 29.6. So still a spontaneous reaction. All right, that's all I got for today.